Functions as power series, Part 1. The basics. Functions as power series. Find the interval of convergence of the power series sum n runs from 0 to infinity of x to the n. We apply the ratio test. You can also apply the root test. In any case, we will get that the L, as we called it, is absolute value of x, and we want this to be less than 1. We conclude that the radius of convergence is 1 and the interval is centered at x equals 0. There are two endpoints then. One endpoint is x equals 1. We will replace x by 1 and we get this. And the other endpoint is x equals negative 1. When we substitute negative 1 for x, we get that. In both cases, we observe that the limit n approaches to infinity of the term in absolute value is 1. So it's not 0. So it's clear that the power series is divergent at x equals 1 and at x equals negative 1. And we can conclude. The sum x to the power of n is absolutely convergent for x's such that x in absolute value is less than 1, and is divergent otherwise. Now, by replacing x by r, we get a geometric series. Let's do that. And also we know that if we have a geometric series with r in absolute value less than 1, we have actually the sum of the series. So we know that the sum of r to the n when n runs from 0 to infinity is 1 over 1 minus r. Now we will go back to x and we will get that for any value of x which is in absolute value less than 1, the sum runs from 0 to infinity of x to the n, which is also 1 plus x to the power of 2 plus, is 1 over 1 minus x. This is a power series which is also an infinite polynomial. This is a function of x. And here we have a description of the values for which the power series equals f of x. Many functions can be expressed as infinite power series which are infinite polynomials. Polynomials are easy to work with. They're easy to differentiate and integrate. They are continuous and differentiable as many times as we like. Replacing complicated functions by infinite polynomials is one of the most useful tools in mathematics and all applied sciences. Example: express the function f(x) equals 1 over 1 minus 3x as a power series. We're able to manipulate a non-power series that is written above using a substitution of 3x for x. Okay, let's compare. You can see that the function f(x) is exactly 1 over 1 minus x with replacing x by 3x. So this is also true when we have the summation. So we are replacing x by 3x. We are going to rewrite it like this. And now we like to know for what values of x the series converges. Here we see in the original series that x in absolute value has to be less than 1. But because x was replaced by 3x, we know that the new series for fx absolutely converges for absolute value of 3x less than 1. And we get that the series absolutely converges for absolute value of x less than 1/3. So r is 1/3. We conclude. For x's that are between negative 1/3 and 1/3, the function 1 over 1 minus 3x is also the power series of 3 to the power of n x to the power of n and runs from 0 to infinity. Example. Express g of x equals 1 over 8 minus x cubed as a power series. Again, we are going to manipulate the given series on the top right. Because I would like to get something that looks alike, like what we have already, which is 1 over 1 minus something, I'm going first to distribute the 8 to the denominator to get 8 times 1 minus x cubed over 8 instead of 8 minus x cubed. The 1 over 8 will be separated now, and I really want to focus on the other part, which is 1 over 1 minus some expression of x. So let's find the substitution here. Okay, you can see that x is replaced by x over 2 cubed. So we get 1 over 8 times the sum of x over 2 cubed to the power of n. I'm just replacing x by x over 2 cubed. Will I write that as this? 1 over 8 is a constant, so I can definitely write it outside of the sigma notation or in the sigma notation. I also rewrite x over 2 cubed to the power of n as x to the power of something over the rest, because I would like to isolate x to the power. Now I'm going to combine the 8 with 2 to the 3n to get 2 to the 3n plus 3, because 8 is 2 cubed. And now I really would like to find for what value of x's the series converges. Absolutely converges for all the values of x's such that x over 2 cubed is less than 1 in absolute value, because the original function was converging for all x's that are in absolute value is less than 1, and x was replaced by x over 2 cubed. We're solving that, and we get, first of all, that absolute value of x cubed is less than 8, and x in absolute value is less than 2. We conclude that the radius of convergence is 2, and the series converges for x's in absolute value less than 2. We found out that for all x's between negative 2 and 2, the function 1 over 8 minus x cubed can be written as a power series. The power series is the sum, and runs from 0 to infinity, of 1 over 2 to the power of 3n plus 3 times x to the power of 3n. Be careful. Let's observe our last example. We can substitute, for example, 1 for x to get g of 1, and if we will replace x by 1 in the expansion as a power series, we will get g of 1 written as a series. Note that there's no x's in this one, so this is just a series, not a power series. We can also do the same if x is replaced by negative 0.1. What happens if we replace x by 3? It looks that we can just substitute 3 for the x, but this is wrong. Because x equals 3 is not between negative 2 and 2. The series for G3 is not convergent when x equals 3. So it's not allowed just to substitute 3 if it is out of our set of x's for which the series is convergent. This makes this totally wrong. The end.